We're going to start off with a very interesting presentation. For the price of one, we get two lecturers, Martial and Pierre-François. How are you doing, guys? You're going to have 30, I'm going to look back, but I'm looking at you, I'm pretending. So you're going to have 30 minutes. So try to stop after about 25 minutes so we have a few minutes for questions.
No problem. Can you hear us okay?
I think so.
Okay, good.
Okay, go on, please.
All right, so we're going to try to share that. Okay, sharing presentation. Okay, can you see anything?
Yes, we can see something.
All right, good. Thank you very much. So thank you very much to the organizers for having us to this conference. We are very sorry we couldn't make it to Uppsala, but hopefully next time. Yes, so as Roland said, he's going to have two speakers for the price of one. So hopefully we are good enough for the price. So yes, so what we're going to do today is to talk a little bit about benchmarking multi-configurational methods for vertical excitation energy. So we'll try to make it not too boring. Okay. Okay, so just for as an introduction, you probably all know that picture from Peter Elliott now. That's this very famous zoo of functionals that comes from DFT. So DFT is nice and you can get some very good numbers sometimes, but the main problem is that you have to choose the good functional, and sometimes it can be very tricky because the accuracy of your results can vary a lot depending on your choice. And we usually make fun of those people, but actually, if we do the same for ab initio wave function methods,
sorry guys to interrupt you. We're seeing a join a breakout room menu in the center. Take it away, please.
No, that's us.
That's us, okay?
So you can see the slide?
Yes, please.
Okay, good. All right, so we're making fun of DFT people, but we have basically the same problem. And here you can see that it's not an exhaustive list, but I've tried to gather a few excited state methods, and you see that we can have the same problem. And again, depending on the choice, your choice of methods, you may have results that are good or very bad, actually. So we have to be very careful. And so, for example, the other thing that we could mention as well is that actually ab initio methods are not always more accurate than TDDFT. And for example, here are two examples over here, but you can see that if you choose the right functional for your TDDFT calculation, you may actually have an accuracy that is very similar to couplet cluster or ADC2 methods, okay? Second order, of course. All right, so if you want to have a fair comparison and to learn stuff about your methods, what we usually do is benchmarking. And so if you do benchmarking, really like what is very, very important, I think, is to have very reliable reference energies. So having like numbers that you know are very good, very accurate, as close as possible from full CI. And so that's why a few years ago, and thanks to Denis Jacquemin, so our collaborator and nonetheless friend, we started like building what we call now the Quest database for excitation energies, which are vertical excitation energies. And actually, the idea was to provide to the community, to all of us, a large set of highly accurate excitations energy for a large set of excited states. So not only singly excited states, but doubly excited states, small molecules, large molecules, and so on. And so now we now have like 600 excitations energy that we think are very accurate, that are divided in different sets. Now we have 7 sets. And now I'm going to talk a little bit about those sets because we're going to use them to actually benchmark CASPT2, CASPT3, and NEVPT2 afterwards. So this database was basically, we were able to get those very accurate excitation energy thanks to what we call selected CI methods. So why is because with selected CI methods, we were able to get basically full CI quality excitation energy for small molecules. And that was really like the driving force behind the creation of this database. And this has been possible thanks to Quantum Package, which is a software that is developed in Toulouse by Anthony Semana, that you've heard yesterday talking about the T-Rex IO. Also Emmanuel Giner, that is now in Paris, and Michel Caffael, as well, who's in Toulouse. Okay, and thanks to Anthony's implementation of selected CI, so we use a method that he calls SIPC, which is just one type of selected CI. We were able to get a very accurate vertical excitations energy for small molecules. Okay, so thank you to them. So the first paper is from 2018. So that was the first paper where we use actually selected CI to get those excited states energies. And the first paper was basically including like 110 vertical excitations energies that we're going to abbreviate by VTEs in the following, and oscillator strength as well in 18 small molecules from 1 to 3 non-hydrogen atoms. Okay, so it was really small molecules, accurate geometries based on usually CC3, so third order couplet cluster with a triple zeta augmented basis set. And basically at that stage, we had only like singly excited state and a very few doubly excited states. Okay. And so the idea was to basically combine the best that we could do, and in that case, it was basically full CI to provide what we call TBEs for theoretical best estimates. So that's our reference values, okay? So those reference values, usually they are given in the aug-cc-pVTZ basis because it's a good compromise in terms of accuracy and cost. But sometimes we try to give like complete basis set limits. So when the system is small enough, so we can, okay. And based on those reference values, we could actually benchmark popular excited state methods, including double and triple excitation. So couplet cluster, ADC, and CIS parentheses D, or whatever you want, okay. So for example, we discovered that CC3, for example, is usually very accurate for singly excited states. And so with time, we started like building up this database. So the second set of excitations energy was basically trying to include doubly excited states in the database. So that's what we've done in 2019 with Martial, Anthony, Michel, and Denis. And here the idea was to try to have more variety in the database and have those very challenging doubly excited states that we know that methods like TDDFT cannot do, for example. So here again, based on mostly full CI, but sometimes the molecules were too large, so we relied on couplet cluster or multi-configurational methods to get the TBs, okay? Still large basis, and we started like benchmarking methods that are at least triple excitations, because for doubly excited stage, you cannot rely on something like that only has double excitations too bad. Okay, so you need at least triples, but even quadruples are even better. And we included as well benchmarking of multi-configurational methods. So third one was basically try to increase that database to have something like quite exhaustive. So we started like increasing the number of excited states, so mostly singly excited states in slightly larger molecules from 4 to 6 non-hydrogen atoms. So now it's too big, so we cannot rely on SIPC or full CI for the TBEs. So we started using CCSDTQ, so EUM CCSDTQ or EUM CCSDT, okay? So here, when you get to CCSDT, it starts to be so-so in terms of accuracy. You can't be sure that you're really chemically accurate. So very recently, we started to go to quadruples, and we recently improved those TBEs based on CC4 or EOM-CC-SDTQ. Okay. So that's the idea. So I'm not going to spend too much time. I don't want to bother you too much. But after we improve that again by including what we call exotic molecules. So it's probably not the right term. So I'm not talking about the pineapple molecules, but it's more like we had like closed shell molecules with fluorine, chlorine, phosphorus, silicones, slightly different for carbon, oxygen, nitrogen, and hydrogen. We included some radicals as well, so doublet-doublet transition that can be very challenging for some of the methods. Okay, and we could test the differences between unrestricted and restricted open shell formalism. And afterwards, we trying to get more and more larger and larger molecules and try to have more excitation. So that was this paper, and the latest one was basically the penultimate one was trying to improve that again because we were missing some charge transfer excitations. So that's something that we did very recently with Denis Jacquemin and Xavier Blaz. And here the feature is that we started benchmarking TD-DFT, and the beta salpeter formalism based on from many body perturbation theory. Okay. So the latest one was this one, and basically it gives us 600 or 700 excitations energy to play with. All right, so you're going to tell me that picking in 7 papers data if you want to do your own study, it's a bit annoying. So thanks to Michael Berry, who submitted his PhD last year, he created an entire new website. And the address is here, where you can basically, so it's an interactive website where you can download the geometries, select the molecules that you want to study, select the type of methods. It's all interactive, and you can do your plots. You can calculate your statistic quantities if you want. So if you are interested by those kind of things, have a look at the website, and you can even contribute to the website. It's an open website. You can do some pull requests if you want to do some updates or additions and so on. So please have a look and let us know what you think about it. All right. So lots of people have actually used that website. So for example, a few examples here, Martin at Gordon's group has been using the Quest database for orbital optimized DFT and TD-DFT. Martin Kops to assess hybrid functional in TD-DFT. The Kalai and Goris group are using this benchmark, those reference data to benchmark double hybrids as well. And they have done lots of papers on this. Eric Noskamen's group is using that for QMC, for doubly excited states. Claudia Filippis and Anthony Semama's group are also using that for some of the data to test the QMC for excited states, and Tim Gould for ensemble DFT. And our group as well are using that a lot for wave function methods to benchmark them and many body perturbation theory. So here are a few examples. And Martial is going to take over now to talk about using that database to benchmark CASPT2, CASPT3, and so on. Thank you.
Okay, thank you, T2. Sorry, I'm just going to share this other document now. Okay, so what I'm going to present now is an illustration of how we have exploited this theoretical best estimate that are collected in the Quest database to benchmark multi-reference perturbation theories for the calculation of vertical transition energies. So we have selected a subset of the molecules reported in the database containing 3 non-hydrogen atoms up to 6 non-hydrogen atoms. And for these molecules, we have computed about 280 vertical transition energies. Among these vertical transition energies, you have 174 transitions to singlet state, 110 transitions to triplet states. You have also various type of excited states. You have 206 transition to valence of valence type, 78 Rydberg states. And among the valence states, you have n pi star, pi star, and a few double excitations as well. So We have performed different kinds, flavors of multi-reference perturbation theory. We have used NEVPT2 with augmented CC-pVTZ basis set, the frozen core approximation. And we have used two different versions, the strongly contracted and the partially contracted versions of this NEVPT2. All these calculations are state-specific calculations. We have done also state-specific calculation with CASPT2 and CASPT3 with same basis set, frozen core approximation. We have tested the use of the IPEA shifts, and we have used some level shift to alleviate the problem of the intruder states. All these calculations have been performed in MolPro. And of course, one of the critical steps in all this calculation is the choice of the reference CASSF wave function, which means that we have to select the active space and the state averaging procedure. So this is a strategy that we try to follow. We have decided to state average systematically between the ground state and the excited state of interest. This is to minimize the bias between the ground state and excited states. In this way, they share the same set of orbitals, so there is a consistent description of all the states, including the CASSF level. This means that we have state average as well between states of different electronic symmetries, which is interesting in the case where we have doubly degenerate states in non-abelian point groups. And we tried also to choose, whenever possible, an active space that is as simple as possible. So I'm just going to show an example. If we calculate pi star excited state in these thiophene molecules, for example, here the A1 pi stars, there are two excited states of that symmetry for which we had these theoretical best estimates. We did a state average over 3 states because we need to include the ground state, and we took all the valence pi orbitals. So it means we distribute the 6 pi electron in the 5 pi orbitals. If we want now to calculate a Rydberg state, pi to 3s of A2 symmetry, then we need to add this extra orbital in the active space, the 3s orbital here. And then we have a state average over 2 states because we want, again, to include the ground state in the reference calculation. So we distribute then the 6 electrons in 6 orbitals in this case. Okay, there are much more complicated cases that I'm not going to describe, but this is the, let's say, the systematic strategy that we try to follow to keep things as simple as possible. Okay, I'm going to show you now the results. I'm not going to obviously talk about each molecule individually, which will be far too long and boring. So I'm going to show you global trends for this, well, for the error distribution for all these theoretical levels. So here I report in this table the errors for the various levels of theory. And I'm going to focus mainly on the MSE, which is the mean signed error, the MAE, which is the mean absolute errors, and max plus, max minus are the maximum deviation. So the largest positive deviation and the largest negative deviations. And here you have the histograms of the error distributions for these various levels of theory. So I'm going to talk discuss about all these. First, CASSF, as expected, we have a large average error, about 0.5 EV. It's nicely centered around 0, though, which is nice, but then, of course, the maximum errors can be very large, up to 2 electron volts, which is rather expected at this level of theory. Now, when we include the dynamic correlation at the CASPT2 level, let's start with the case where we don't include the IPEA shift. Of course, the average error is much better, but still quite substantial, around 0.3 EV. And we can see that the distribution has moved to the left. So we systematically underestimate the vertical transition energies in this case. So the mean signed error for this method is minus 0.26 electron volt, which is not satisfying, of course. When we include now the IPEA shift, then things get much better. We have a nicely peaked centered distribution around 0 and a much smaller average error of 0.11 electron volt. If we look now at the NEVPT2 calculations, so the partially contracted NEVPT2 is here. It's rather similar to the CASPT2 with IPEA, maybe slightly larger distribution, and also the mean sign error is a bit more positive, which means we overestimate a little bit more the vertical transition energy, but it's quite competitive with CASPT2. In the strongly contracted version, it's a bit inferior in terms of results. The average error increases slightly, but it's still also quite nice. Now, if we move to CASPT3, which are these two histograms here, the first striking result is that it doesn't depend much on the IPEA shift. Yeah, so which means that CASPT3 is less sensitive to the reference zeroth order Hamiltonian. The best result is actually obtained without the IPEA shift, and we see that it's a slight improvement compared to the CASPT2 result with IPEA shift, with a slight decrease of the average error, and the mean sign error as well decreases slightly. Okay, now if we look at this error distribution for the different type of transitions, here I report at the top the distribution for the singlet transition, then the triplet transitions, then valence transitions, and Rydberg transitions. So we see that for this multi-reference saturation theory calculations, we have a consistent description of all these transitions, which means that we have a nice distribution of the error, whatever the type of transitions. We can observe that it's slightly more accurate for triplet transition than for singlet transitions. And the accuracy is very similar between valence transitions and Rydberg transitions. Of course, with CASPT2 without the IPEA, it's also systematically underestimate the vertical transition energies for all type of transition, apart from the Rydberg transition, which seems better described. Now, if we look at the trends with respect to the system size, so here at the top, we have the error distribution for the 3 non-hydrogen atom molecules, and then 4 non-hydrogen atom molecules, and then the larger one at the bottom. We see that the average errors, whatever the method, CASPT2, CASPT3, increases as the system size increases, which is not so surprising, obviously, as this means that the active space with respect to the system size is smaller as the system size increases. So things tends to deteriorate, which is also visible at the CASSF level, of course. And the other thing that we can notice is that CASPT3 for the larger systems is barely better than CASPT2. We have almost the same average error. Now, this is just a slide to show you the timings and the comparative timings between CASPT2 and CASPT3. We took the example of a calculation on benzene with different size of active spaces. And we see that the ratio between the cost for CASPT3 and CASPT2 becomes important when the size of the active space increases. So which means that CASPT3 becomes rapidly unfeasible for large active spaces. And considering what we just said before, for the larger system where CASPT3 doesn't improve much, the result compared to CASPT2, it's probably not worth the extra computational effort, at least for these large systems. If we look at the error distributions for the CASPT2 and CASPT3, we see that there are a number of transitions for which we have still very large errors with deviations, errors above 0.4 electron volt. And I report here the list of these excited states which cause this kind of problems. So they are all pi-pi star transition, and these pi-pi star transitions are in fact ionic, correspond to ionic states for which the active state that we choose, mainly valence pi active orbitals, is insufficient. So I'm just going to show you that we can systematically improve this result if we want to, of course, but we have to push and better describes the reference wave function by including in particular sigma orbitals, because we need to, in this case, to describe the sigma pi correlation. So I took the example of the second B1U state of pyrazine, for which we have an error of about 0.6 eV at the CASPT2, CASPT3 level. And that was obtained using a valence pi active space and adding some 3p orbital for radial correlation and to describe the Rydberg state that is present as well. But in doing so, we have some artificial mixing between the valence and Rydberg states. So what we have to do is to include the sigma orbitals in the active space. We did that at the RASSF level, including the sigma in the RAS1 and sigma star in the RAS3 space. And then optimize the orbital so that we remove this artificial valence Rydberg mixing. And in this case, if we use the RASSF optimized orbital to compute our CASPT2, CASPT3 vertical transition energy, things are much better within 0.1 eV of the theoretical best estimates. Okay, to finish, we have shown that the IPEA shift is important for CASPT2, but it's not necessary for the CASPT3 calculations. The CASPT2 with the IPEA shift has a good accuracy with an average error of about 0.1 eV. The partially contracted NEVPT2 is quite competitive with CASPT2. The advantage is that you don't need to include shift, and it's a bit faster as well than CASPT2. The strongly contracted version of NEVPT2 is not as good, but still quite competitive. And CASPT3 without IPEA gives slightly better result than CASPT2, of course, at a certain cost. And I didn't discuss that, but I show here some comparison between the error distribution of this CASPT2 and FPT2 with other single reference method, and in fact, CASPT2 has a similar accuracy to CCSD, and is a bit better than ADC2 and CC2. But of course, the advantage here is that we describe also a double excitation, which is not correctly described at these levels of theory. So among the perspective, it would be interesting, of course, to investigate the multi-state version of CASPT2. Also include perform calculation for larger system. So T2 mentioned that there are some data for charge transfer excitation in pi-conjugated system, bicyclic systems. So that may be something that we'll be doing in the future. And of course, it would be highly interesting as well to benchmark this method away from the ground state geometry to investigate, for example, the photochemical processes. So this is probably something that we will be looking at in the future. Thank you very much for your attention. And if you have questions, then we are happy to try to answer. Thanks.
And you're very on time. I'm very grateful for that.
No problem.
So I open this presentation for questions. Yes, please.
With Hugh Burton, you published this one very nice paper where you try to raise attention for the fact that you can actually resum the series. Given that for CASPT2 you only have two terms, it of course doesn't really make sense to do the 0-1 Padé approximation. But now that you've gone to CASPT3, or there are also contributions with NEVPT3, does it make sense to use these resummation strategies, or are they mostly superfluous?
So you're talking about resumming the perturbative series, right?
Exactly.
Okay, yeah. So we actually try to play some games with the data, and as you said, there is no enough terms in the series to try to do resummations. If we could have access to fourth order, maybe it would be useful, but here 2 terms is too few. So we could try to do a few things, but it's not worth the price yet. So yeah. But of course, it's so the radius of convergence of the CASPT-N series seems to be much larger than the MPN radius of convergence, but we need more data to be sure about this. I don't know if it answers your question.
Thank you very much.
I have two questions. So the molecules you have been benchmarking on are typically molecules where DFT or any other method like coupled cluster will do fairly well, but the challenging systems like transition metal complexes, will you include those in your benchmark suite?
So, I mean, as far as CASPT2 calculations are concerned, yes, we do plan to compute larger system, and in particular transition metal complexes. I'm not sure now how we will get these theoretical best estimates with these coupled cluster methods. Maybe T2, you can answer for that.
Yes.
Some of the systems, at least, they know the energy difference between the different spin multiplicities.
Yes, so we just started actually including those systems. We haven't finished the calculations yet, but that's something that we had in mind for a very long time. But it's actually harder to find some interesting system for transition metals that.
Right. That's also going to sort of address the problem that some people tweak the IPEA shift to 0.75 when they do transition states.
Yes.
Another question. So there has been enormous development of the CASPT2 method the last few years. There are different new zeroth order Hamiltonians, like for instance, the CASPT2K version that is in Orca. There's also the CASPT2G version, which is in open multicast, that maybe should be dusted off and looked at. And also you talked about you're going to benchmark the multi-state version. I hope you with that include a whole new family of different multi-state versions, like the extended, the ordinary, the rotated, and the extended density weighted.
No, so I didn't say I would do it anyway. I said it would be interesting to do.
Well, I'm tell you why you're going to do it. You showed problematic cases where you had artificial mixing at the CASSCF level.
Yeah.
And the way you solved it was to increase the active space. Another way to solve it is to compute the corresponding state with the anti-symmetric rotation of the two states and have them to be resolved properly at the multi-state CASPT2 level.
Absolutely, yeah. Yeah, so the main, well, it would be interesting at least to look at these particular cases where the state-specific CASPT2 or CASPT3 fails with multi-state. Otherwise, benchmarking all this transition with multi-state is a huge work, because obviously we have to merge some of the active space to treat all the states simultaneously, at least in the same symmetry. So it's a lot more work than what I did so far with this state-specific. And as you said, there are many flavors of the multi-state CASPT2. So, but it would be highly interesting. I agree with you. Yeah.
Yep. I think there are people here in the audience that might be interested to pitch in and help if you dare to ask.
Thanks.
We're a bit behind on the schedule, so if you want to chat with these two guys and come with proposals, do it on the chat. And thank them again for their nice presentation.